Well, I think gonna start if you don't mind. So, Esther, Aritz, can you please pass the next slide? Yeah. Okay. Thanks a lot for attending this this webinar. This is the first of the second year that we started. We started these seminars with the pandemic, so I think it was also a nice initiative because we're inviting very interesting people, researchers that are doing very nice and very good research, and that's for us an honor and a pleasure to invite them, providing many insights and thoughts about the current natural language processing technology and also language technology, and not only NLP. Our research center is also on keen about speech and all about also related to artificial intelligence in general. So these webinar series are organized by our research center. It's a Center for Language Technology, also in conjunction with Deep Learning for Natural Language Processing course and the master that we are also collaborating is an international master, Erasmus Mundus Master in Language Technology. This second year, we have invited Xiang Ren, who is also participating in this seminar because of his research topic. I think it's very interesting, and also is also hot topic now in the research area, our research area, which is common sense and reasoning research. And he's starting this second year, and he is coming from the University of Southern California, and he has been also in collaboration with many researchers, also in the Allen Institute for AI, so and many other initiatives. And so his background is also his research background is very interesting. So I think it's a pleasure for us, and I hope a pleasure for you also to receive his talk. So to listen now what he has to say about the common sense reasoning in the world, which is, I think, it's a very interesting research topic. So after that, we will have Beret Schwartz, who has been also involved in common sense and reasoning research topic. And later on, we will have Marit Koponen. And we will continue with more talks, one per month, more or less. And we hope that if you are interested, you can also participate in that. So thank you very much, Xiang, for accepting to be part of these seminars. And I now give you the floor. So thanks a lot for accepting, and good luck with the new starting with this webinar series second year. Thank you very much.
Thank you, German, for the intro and the invitation. I probably need permissions to share the screen again. I find it not able to share at the moment.
Yeah, in a minute, we are going to have you the floor.
All right. Cool. I think this should be coming up. All right.
Perfect. Yeah.
Perfect. Hey, all right. So I'm glad to be here virtually and sharing my work. I've been working on common sense reasoning for a few years, and I've been talking to many practitioners, and always find there's a gap between like the research results and actual sort of issues when they deploy these systems in the real world scenarios. So that sort of like motivate the title and the thing of my talk, common sense reasoning in the wild. Right. So when I say common sense reasoning, the main reason actually drive my research in this space is language. And in particular, we human might not even notice too much that our language and text data is often ambiguous and underspecified, right? When my friend texts me and say, let's hoop at 10, Sam Park, we can actually figure out what does 10 mean here easily. Or when we are sitting in front of TV with our family members watching a singing show and seeing these images, for example, and someone say her voice is amazing, we probably don't have any difficulty in figuring out what does her refer to in this image in the TV. And what's happening behind the scene is that a lot of presumptions has been made by people in the room or around you without too much of like heavy communications in explicit words. For example, we know in the first example that meetings usually specify place and time can be referred by number. Therefore, this is usually the 10 here very likely refers to time of the day. In the second examples, person holding a microphone will be like the highlights in the scene, and standing on the stage in front of audience is likely speaking and singing. So then her becomes like easier to be inferred in this image, right? So that's the kind of the ability of making presumptions for daily kind of scenarios, and communications is a really important abilities for human. And we've been doing a lot of research putting the frontier about machine having this common sense ability or machine common sense. And there seems to be a great growth of number of works, research results, and also so-called performance on this like benchmark data sets for common sense reasoning tasks in the past few years. For example, if you're looking at this common sense QA question answering data sets, which is one of the most kind of adopted data sets in many of the research papers for studying common sense reasoning, there seems to be a huge progress made in the past 2-3 years in terms of the performance or accuracy numbers grow from 50-ish to beyond 80 or even close to 90 in the last year. If you try GPT-3, for example, and that seems to be saying like, maybe day one you are working on a research benchmarks for your PhD thesis, and then in the next week you find out some big systems based on maybe pre-trained language model actually have a close to human or even superhuman performance. And that seems to say like, oh, you probably need to switch a data set, or like otherwise you're gonna be stuck with your PhD thesis. But is that really the case? Of course, no one wouldn't talk about natural language processing ability without talking about GPT-3, which can do a wide range of different tasks, including the common sense question answering problems that I just pointed out. So the broader question, of course, everyone will be asked about or will be talking about is like, would this like gigantic pre-trained language model paradigms is a right way to achieve machine common sense? And my argument here, of course, wouldn't be interesting if I say yes, but I'm gonna just talk you through with some of my observations in the past 2 years about why I think there's still a lot to be done in terms of framing common sense reasoning problems for these machine models, and what is the important aspects to look at when we evaluate these systems to really measure the progress of machine making common sense reasoning in like a human-like reasoning manner, and also can actually work for many of the real-world challenges we can observe. But before that, let's play a little bit with GPT-3 to see how far it can go. So on this problem, so we already know like reading comprehension, especially about like factual knowledge type of reading comprehension problems, is a strength for this big language model because they pre-train from large corpus, encyclopedia of corpus like Wikipedia. So the first two questions about factual knowledge doesn't really be difficult cases for GPT-3. And even sometimes we see GPT-3 are able to say unknown or like unsure about the questions. It has certain ability of abstaining for answering things, which is great for safety and sort of reliability consideration. You can even ask GPT-3 some really like common knowledge, like numerical knowledge about entities and concepts, like how many legs do cats usually have, or like how many legs do ants usually have. They have no problem answer some of these questions. That's one task we have done in the Commonsense benchmarks published 2 years ago. But now, if you make the question a little bit more like funky and ask things like, how many wings do tigers usually have? This is kind of a tricky question because things got mentioned in the sentence are still very common words. I don't think machine has any problem understanding these keywords like wings and tigers, and might be able to associate knowledge about it. But the thing is tricky is because in Commonsense, no one will actually talk about tigers having any numbers of wings. They will only, because we know they don't have wings. So this piece of this information and discussions wouldn't show up at all in most of the text data that's out there in public, and then for the model to learn from. So what happened here from GPT-3 is there's a reporting bias going on where GPT-3 often see wings associated with the number 2, but on the other objects like birds and so on. And it just learned that piece of facts and use that to answer regardless of thinking about whether tiger is compatible with this piece of facts of like having wings. So this is just like a small evidence showing like the model is learning in a certain manner, but it's far from having the type of common sense we human usually agree on. Again, going back to the discussion on this like high numbers achieving in the public benchmarks nowadays, I think what's really going on there is an oversimplification of the evaluation in our research community and also the practical applications. There's pros and cons about simplification of these problems. First of all, we can really make progress by making a bunch of assumptions and create a data sets to model the progress. But here we are in the stage where this simplification seems like too much for our current machine models and language models. One of these major kind of assumptions and simplification we have made so far is the ID distributions between the training data split and the dev and test splits when we are creating data sets. We know usually what happens is human annotate or crowdsource answers to the questions and then just have an ID split. And that seems to be no longer a big challenge for the machine systems to learn model shortcuts or spiral correlation patterns to actually fit the training data sets, which turn out to fit the test set very well. So I'm going to argue certain points that really differentiate how the current benchmarks is focusing on or like is created towards versus what the challenges we often will see when deploy these common sense reasoning systems in the wild or in the more practical scenarios. First thing is ID splits can easily benefit models who are good at learning shortcuts, while ignoring the fact that in in real world inference time scenarios, there's a lot of linguistic variations what happens where these shortcuts no longer apply. And this kind of behavior is not widely adopted in the current design principle of test sets, right? For example, in our Ricard paper 2 years back, we showed that by just perturb this knowledge statements with different surface phrases and words or even different orders, but preserving the knowledge, the inference logics in the sentence, will create a huge challenge to current language model to understand these like linguistically varied but logically preserved perturbations. And then we also find out current system is really struggling with underspecified inputs or adversarial inputs. And there's already some effort starting 2 years back to capture these behaviors. We really want to understand systems can do divisible inference and non-monotonic reasoning kind of behaviors which humans are really good at. For example, posing a question about when is Super Bowl in the search box without specifying this is likely referring to the Super Bowl this year versus previous year is some capability we can have when we have these daily conversations between friends. But we hope the system can be tested or evaluated more towards these kind of challenges. And lastly, our evaluations are very customized and specialized for individual tasks. Let's say classification tasks of a certain label space, and when you have a different data set, you start switching the label space to a different set of Go label. That's kind of the traditional way of doing the evaluation in our community, and doesn't really consider in the fact that when we try to test common sense reasoning, we might care about both the discriminated tasks format and also generation task format. Even for generation task format, we could have like closed book question answering, other type of question answering task. We really want to see like if we have the same piece of knowledge, for example, would this same piece of knowledge be captured by the machine models even under different task formats, right? I think this kind of challenges is understudied in the current community. So accordingly, in this talk today, I can walk you through a few efforts we have done in terms of just making things a little bit more closer to the performance in the wild perspective that I just introduced. For example, we would talk about work that trying to go from this closed-ended reasoning, which is like multi-choice QA, choosing answers from 4 or 5 options, into more open-ended reasoning, such as like composing a sentence with a few concept keywords that are given. We'll show you a work where we trying to probe the model's reasoning ability when we start perturbing the sentence to preserve its knowledge or its logic, but changing the surface form order to see if the model really understands a piece of common sense inference knowledge, for example, like the relations between tree and fruits, for example. And lastly, I can show you about recent efforts where we try to test the NLP model for their so-called cross-task generalization ability, which is like just like human, we learn smaller tasks first, and then we use the skill we learn from those tasks to learn unseen tasks or new tasks more quickly. This kind of behaviors, whether it exists in the current large language models, that's an interesting question we asked. So let's start with the open-ended reasoning problem. If we look across board how we have evaluated the common sense of language models, we see many 2 threats. One is probing language models by framing these like mask prediction challenges by masking out some keywords like numbers in the sentence, and then probe the language model's prediction probabilities over these mask positions and see if it aligns with humans' estimation. We also see a lot of work, actually maybe over 70-80% of the papers published in the last 3 years about common sense reasoning are framed as like a multi-choice QA question, where like there's a question with or without a passage as context, and then you choose answers from 2 choices, 4 choices, or 5 choices, and so on. right? Obviously, we see the gap between what's going on in these benchmark data sets and what is going on when we try to deploy common sense as a service in the real world application. In many real world applications like dialogue systems, robot planning, even search engines, there's no choices given ahead of time to the agent. There's most likely conditions framing as natural language, text, and a bunch of other structural, unstructured signals are given, and likely you are to produce a sentence or some instructions as follow-up. So the search space for the problem are rather different from this closed-ended reasoning problem. So what we propose here as like a pattern kind of efforts few aspect along with our collaborators at AI2 is to frame a problem that happens very commonly in our daily lives, which is look at a bunch of common objects like dog, frisbee, catch, and throw, and try to compose a sentence that is both grammatical, fluent, and also plausible in terms of common sense, like a boy throws a frisbee and a dog catches in the air. So we want to give the same challenge to our big language model and see how they're doing right now. Right, that's the Common Gen paper, where the input is a set of concept words. These could be objects, could be actions, and the output is a sentence describing everyday scene using all the concepts. So technically speaking, is a lexical constraint text generation problem. We can see like human easily can compile a lot of diverse sentences. Like another example is like a dog catches a frisbee and when a boy throws it. Machines is doing okay, but not good enough on this task. At the time when this paper was published with tests on T5, it gives sentence like dog catches a frisbee and throw it at a dog, which sounds amazing. There's no grammatical errors here. It's just like not that plausible to humans, right? The way we create it is we have a human curated test sets, which is about 1,500 number of concept sets, unique concept sets. And then we have a similar size of depth set and much larger training set, where the training set is created automatically using caption text from image caption corpus. So you can argue that there's a big distribution shift between the training and test set here, because test set is totally human authored sentences and training set is like more artificial sentences that was collected from caption text. And this is one interesting challenge, and we see a lot, it creates a lot of like generalization challenges to current system. Another challenge is like, we try to make the concept sets has less overlaps between the chain and test splits. So you will see many of the concepts, but the concept combinations are very likely unseen when you move on to the depth and test set. That's another sort of non-IID sort of simulations we're doing here. And it turns out to be a very popular benchmarks in the past 2 years for many people who works on text generations and especially controlled text, constrained text generation. It become part of the upstream data sets used in T0s or GEM benchmarks. A lot of follow-up works that trying to work out methods that can do better on this problem. Roughly speaking, they go from many of them have this like neurosymbolic kind of fashion where they do have an internal structural representations of the concept relations and then go from there to compose the sentence. Among them, there's also our work, which I will briefly walk you through, which we call it scene imagination. This is kind of very much trying to simulate what is going on when people trying to solve this problem. So when we present these concepts, we're trying to connect the dots between them by just visualizing a very abstracted scene and then we're trying to verbalize that scene into sentence, right? So we're basically trying to reproduce this process in a machine manner, which is like we can have a scene knowledge graph first constructed between the concepts that are given, and technically we present this scene knowledge graph as a sort of like a semantic parse tree with these like relation types, and then we go from that scene knowledge graph to produce the sentence. So that means we are breaking this concept to text translation into two parts, where the first part is to generate the graph from the concept, and then condition on the graph, we generate the text. So we call that imagination module and the verbalization module. The main kind of a drive for doing this is that there's actually a lot of interesting data can be collected to pre-train this imagination module. For example, we can take the caption datasets, we can and the story datasets and the scene graph datasets from the vision community to pre-train the imagination module, to equip it with the ability of like turning a set of concepts into some meaningful structure representations of the scene. And then we just rely on some language models to verbalize that structure representation into text sentences. A little bit more details about both the imagination and verbalization modules here are single transform text-to-text transformers like T5. The nice little trick we did here is to use the linearized scene graph representations to make everything into a sequence, so we can do a seq-to-seq generations in both the pre-training phase and also the joint fine-tuning phase towards this common training set. And that turns out to be really helpful because of we explicitly externalize this like imagination step. It helps the generations to be more plausible. Let's look at this example. So we're using these couple keywords without imagination module. It will just give you a sentence like someone opens his shoes and hit a bottle on a wall. It's trying to use the keywords as many as possible, but it doesn't make the right connections between these keywords following common sense. With the imagination module, we first produce a scene graph looking like this. It started looking pretty good because it captured the behaviors like, okay, man can open a bottle, man can hit a wall using shoes, something like that. So this output here becomes like a man opens a bottle and hits his shoes against wall, becomes a more plausible, even though it's not perfect. And performance-wise, we do see something aligned with the qualitative study here. Our method is showing the pink bar here, can outperform all the existing methods except for one, which I would say a little bit why. So we compare with most of these like neurosymbolic text generation approaches like KGBART, Note-to-Text, with CTG that are published almost the same year as our paper or a little bit earlier. We all using this almost the same base model, which is like a similar size T5 or similar size BART, by adding knowledge on top of it. And it turns out our imagination mechanisms is helpful there. The KFC net is a special based on which is using a much larger pre-training corpus, 700 million sentences, versus we are only using a 20 million sentences. So that makes a big difference to the performance. And we actually have follow-up works trying to bridge this gap in terms of pre-training size. Any questions, please feel free to just stop me or just post on the chat if you have. I'm happy to just stop for a little bit questions. Right. So moving on, another thing we talk about just like open-ended reasoning challenges versus the closed set reasonings like multi-choice QA. That's a big kind of threats happening. We also have a few other works other than Commonsense that goes into this direction. But now switching the gear a little bit, we talk about this like logical robustness issues in evaluating language model. And one example that motivate this is like in our daily conversations, for example, you might receive a text from your friend saying, I'm going to sit in front of hundreds tomorrow. And you will say, deep breath, you will do great. And the implicit reasonings happening there is that you know that the fact, a common sense inference fact that performing in front of audience can cause anxiety, and therefore you text back to say deep breath, you will do great. Now, let's say another friend of you texts you something slightly different, saying that she's going to perform in a piano recital tomorrow. Probably your replies will be very similar because the implicit reasoning is kind of similar because they're still like performing in front of audience can cause anxiety. So you would, and also say like deep breaths, you would do great. Right. And what we're seeing here is the fact that not besides the ability to recording and common sense reasoning knowledge to make proper inference here, there's also this like consistency on the inference. Admit that there's a linguistically varied statements, but the common sense reasoning logic, which is showing the blue part, performing in front of audience can cause anxiety, that stays the same. We really want to try to frame a challenge that capture this very subtle sort of ability of human reasoning in the daily scenario. So what we do in this work is to actually start from formalizing the common sense reasoning logic and then go from there to translate these logics into a variety of natural language statements and see how the language models behave over these statements, right? Just to walk you through these, what I mean here, let's say we start with an inference knowledge that if object A size is smaller than object B size, then it's more likely that you can put object A in a container than putting object B in a container because of the size. So there's some common sense knowledge here. It's kind of vague. It's not precise because we don't know the exact size of that container we are speaking about. So we are measuring this more like in a probability manner, right? And what is going on here is like, okay, you can imagine there's two fake objects here shown in this like figure. There's an object called predact, which is just a fake name. It doesn't matter what it called. This predact can be smaller than fluback. So there's some chances, like bigger chances or smaller chances that trigger can be put into this container in the middle than a fluback. Or if you change the size of these two objects like predact and fluback, one is actually smaller than the other, then your conclusions might also change. So you can actually come up all these like common sense, like factual statements in a logical form and then turn them into sentences. And they actually would ask you to predict differently sometimes. But even though the piece of common sense logic behind that is the same. So that's a way to actually study the robustness for these so-called logical perturbations. So to sort of simulate this in terms of creating an evaluation benchmarks, what we did is like we take in an original statements like A is heavier than B, so A is better at syncing than B, and then start adding all sort of logical perturbations like negations to the conclusion part, entity swapping the orders, and using the antonyms in of the syncing. So you can have a set of like perturbations to the original statements And then you're masking out the keywords. In this case, the keywords is the comparator keywords, like better or worse. And now you have a probe set. And these probe sets can be used to probe any mask language models or infilling-based language models like T5 and see how would they make inference in a consistent manner. So that means like you can actually evaluate the accuracy, not just on an individual instance. You can look at the accuracy over a set of probes that belongs to the common sense logic, which is the more strict kind of evaluation. So let me show you what the current language models performs right now. Humans doing pretty well here. It's not perfect, but it's close to 92% here on the human curated set. And it turns out that I think we try up to like T5 large and robust large in this whole study. So what we are seeing is generally all these language models are performing like a random guessing on our probes. And the even more interesting thing is fine-tuning over a training set doesn't really help the language models to do better, which is the thing we want in these challenges, because it means like shortcut learning or surface pattern learning doesn't really solve the data sets. And you have to have those like internal logical reasonings ability to solve the task, it's been evidenced that it's possible given the human performance is very high here. And we look into a little bit more why the models are given random performance. It turns out that the model has a bias on those mask prediction words, like better versus worse. They have like certain bias over certain words, like they prefer more than prefer less, they prefer better than prefer worse. So the performance here can show that. And fine-tuning mitigate imbalance issues, but both of them drop to 50%. That's also quite kind of a surprising here. Lastly, if you break down the model's performance over these different types of perturbations, you can see that the model do a little bit better on without seeing negation and do a little bit better compared to antonyms and paraphrase here. So still a lot of interesting challenges exist in these RICAR data sets. We are having ongoing projects within AI to try to frame some follow-up challenges on top of this, and also trying to build neurosymbolic approaches on top of our large language models to solve this. And also just as a caveat that we also tried GPT-3 on RICAR, and it's also just like 50-ish percent accuracies, which is great. So GPT-3 doesn't solve the data sets so far. Cool. I think I only have like 10 minutes left, so I would use that just to go through the hopefully a little bit on future work, and also this last piece of work focusing on what I said in the beginning called cross-task generalization. So the background here is that most of the data sets we see in machine learning and NLP community is learning at the instant level. So you are working on, say, sentiment classification task, and you look at data instances that are collected from different domains of text, like movie reviews versus product reviews, and you break them into chain and test sets. You mostly are testing the domain generalizations here, versus if you think about something called task level generalization, it will be looking like this. So you have training sets consists of, say, sentiment classification task on movie review domain, and you have reading comprehensions on news, and then you have biomedical relation extraction. They are put into the training set, and at the test time, you are actually asked to work on tasks that's not seen in the training set, which is like paraphrased in identification or common sense multi-choice QA. So this really broadens the scope, where like in the previous paradigm, is just one part of our training sets, if you see it that way. So the CrossFit is making these efforts into a larger scale. So what we we start with collecting 160 different data sets or tasks and turn them all into a text-to-text format, which is a unified format for our language model to learn. And this data sets was collected from Hugging Face data sets and cover a range of things. So for example, we group this task into a 2-level category as shown here. You can see there's generation, classification, QA, and others. And then we have a further breakdown under classifications, for example, like natural language inference or sentiment analysis. Now, the interesting part starts with like, you could follow this ontology to partition the data sets into different ways. For example, one partition is like, you can just classify, you can just categorize the task into based on the first level labels on the ontology. So you have question QA task, conditional generation, classification, and others. And then you can say, I will train my model using maybe 80% of the instances from all of these 4 categories, and then try to see the generalizations to the rest of the 20%. Or you can have another partition saying, I'm gonna use only the non-classification task for training and see how my model can generalize to classification task, which is never seen in the training phase. So the data sets allows you to create and construct all of these interesting chain depth test partitions that can help you understand how the model would generalize across tasks with very much like with bigger dissimilarity or with smaller dissimilarity. So that's actually what we did in this study. So just to give you a little bit more background on the experiment setup of the cross-fit analysis. So of course, we start with a large pre-trained model like T5, and this T5 is then learned on the training split of cross-fit partitions. For example, you can use multitask learning to learn on all of the non-classification tasks. This is called upstream learning. And then at the inference time, you can just fine-tune with few shot examples. You can fine-tune your checkpoints on different test tasks. Let's say a classification test task will be like you fine-tune on the IMDb data sets with 32 examples. And then you will be able to test your model's performance on IMDb test sets. So you can see the main difference is that there's an upstream learning phase, which is like to help the model learn from a wide variety of different tasks that's and then try to see these generalizations or few shot generalizations to an unseen test task. Okay, so we basically follow this experiment paradigm and try to answer a few questions. One question is upstream learning using this diverse task actually helpful for generalization? So we do multitask learning or meta learning during upstream training. And then the finding is yes, and these conclusions holds across a lot of different splits. So what is shown in this table, if I summarize them, is like over 50% of the time with upstream learning, you can get more than 5% relatively performance improvement. And over for 35% of time, you will get improvements within 5%, and only for 12% of the time you will get performance drop because of doing the upstream learning. So that means upstream training over a diverse set of tasks helps the few shot generalizations on a new task. And now the more interesting comes here, which is like, would the selection of your upstream training task influence your generalization performance? So we look at 3 settings. We have more in the paper, but to just give you the concise takeaways here, we try upstream tasks where it's all of them are classification tasks, or it's a mix between classification and non-classification, or it's all of them are non-classification tasks. And for the test time, we just test the model on classification tasks. So we can have a guess here what will happen. Like which of the three settings you think will be most beneficial to the generalizations on the unseen task. You can have your guess here. But the results is actually surprising to us. It turns out that all of these three settings perform equally. Like they bring improvements over the baselines that without upstream training, but they don't seem to be different from each other in terms of how much they will improve. And that's a little bit surprising because we humans might hypothesize that for doing better on classification tasks, I would benefit more from training on classification tasks, right? So maybe people would guess that the first or second settings would do better than the third setting, but it turns out not. They improve equally by 9 to 11%. So there's still a lot of open questions here about why these models are improving. Is that because of the task similarity, which seems not? And it could be because of other like latent skills it learned in the process. So the third question is a little bit more like just applications where we increase the amount of training number of instances on the downstream task or the unseen task from 32 to 64 to 4,000 or 8,000. And we do see the performance improvements brought by the upstream training seems to diminish when you have high resource on your downstream task. But these improvements brought by upstream task can carries over maybe 2,000 training examples. So I would say the takeaway here is like this upstream training paradigm is still very helpful when you are working on few shot or low resource generalizations to a new task. So it's still practically useful per se. Cool. So this part actually leaves a lot of interesting open questions like selecting appropriate upstream task towards a given downstream task. That's actually a follow-up work we are doing. And then task augmentation, continuous learning, task decomposition. All these have some prior work study in a very narrow setting. So these problems can be revisited on the CrossFit setup, which provides you a very interesting test bed. Okay, just to summarize here, since we are almost at time, my research, broadly speaking, is trying to broaden some interesting technique that could really solve the common sense reasoning in a human-like manner, such as like formalizing these inference logics into part of the model architecture, and that belongs to neurosymbolic reasoning. And also, if you understand these common sense reasoning skills as a skills that widely exist in many of the NLP text understanding or text generation tasks, then this massive multitask learning or meta learning, as for example shown in CrossFit, is an interesting way to study how we can distill and learn these common sense reasoning skills from a wide variety of tasks. I'm also interested in like really understanding if the model are reasoning in an intended way or just like doing shortcut learning. So that's to do with explainability and interpretability. And also, I'm very we have a big threads of work which I haven't touched at all today about learning models or updating models from humans' instruction and explanation, which is a more like a direct way of like aligning model behavior with humans' intended behavior. And that together is hoping to build a more trustworthy AI and a fluid human-machine communication mechanisms using our machine models. And I think that concluded talks. Happy to answer questions. I think I looking at the chat box and or Q&A box, so you can also post questions there, I guess. Yeah.
Okay, thank you very much. Very nice talk, and also very inspiring, I think, and also knowing a little bit what you are doing. which is a lot, I think, and also with many insights and many surprising results, like the last ones about the classification things. So yeah, I think it's we have recently with these large language models, we open a kind of Pandora box, then with a lot of interesting experiments to do and insights, I think, and surprising results. And at least for me, it is a very exciting moment because a few years ago, nobody was talking about common sense in the NLP area, and now there is also a thing, machine common sense. I mean, and now people start discussing and producing a lot of very interesting research on that area and that topic. No, so now we can give the floor to the audience. So if you have any question or do you want to make it, you can also open your mic if you want to make a question, and we will give you the floor. Or you can also have questions in the chat if you prefer. So if there is any questions. Well, I have one for you, I think. There is the language models now have a lot of capabilities, and as we see every day that are performing with very, very difficult data sets, also with this multitask and this generalization performance that are able not only to solve particular tasks, but many, many tasks, different tasks, and with very, very good results. And but it seems also that the models don't know what they know, so they still are not. It's kind of probability thing. At the end, they answer correctly, maybe, but they don't know much about that. So they don't know where are they doing wrong, like the tigers and the wings and things like that. So one possibility will be to learn more, not only from text. So which limit? So the question is, to which limit we need to go? So in which? So the question is, how far can we go with language models? And maybe we need to go now for multimodal models, like with pictures, videos, etc. Is sufficient text, or we need to go directly to another modalities?
Yeah, that's a good question. I'm hearing that question. So yeah, my take on this is like, I think there's still a lot to be extracted from these like large language models based on what we are doing so far. At least like I think there's two related problems to what you asked here. I mean, even without talking about multimodal part. So even just on the like text language model alone, I think that there's this problem of like a model uncertainty estimation, which is not very is understudied. So these models right now, you usually will fine tune them to do a discriminative task, like choosing saying yes and no, or choosing from a limited number of labels for predicting an instance. And many times these models are encountering like examples they are not even unsure about what it means, or like it doesn't make sense to them. So they shouldn't be predicting any of the labels. They should be just like they should choose to like not predicting anything for those instances. This kind of abstention ability is not very well studied for language model. And that's to do with the reliability. I think this is just like a side kind of discussion to your problem. And a more relevant discussion to your problem is like, I think probing these large language models, especially those like autoregressive models like GPT-3 or OPT model, it's still a very engineering kind of a practice so far. People play with different demonstration examples or different prompts. They might sometimes get a the knowledge out. Sometimes they don't get the knowledge out. They just treat, right now we're doing this in more like a black box manner, hoping that spend another 2 hours, we can get better results from the model. I think that's mostly what happened. But we are lacking of some tools or principle approaches that can guide us extracting the knowledge out. So one related projects we are working on now is to, for example, using these like uncertainty estimation mechanisms I was talking about to select demonstration examples of probing templates, which are able to make the model to be more confident on the things they are reasoning about. So that's I feel like a interesting directions to move it forward. And also related to this, we also seen people been doing a lot of these like self-rationalization efforts, like the chain of thought paper. And it turns out that magically asking the model to rationalize like what is going on, it seems like helping them to predict the results more accurately. We don't have very clear understanding on that. And my labs has a pilot work showing that these models like rationalization doesn't necessarily be consistent with the predictions they are given. Like they can answer the question in one way, but they can explain the problems in another way, which is still like a mystery. So basically, like we don't know why this rationalization process helped the answering, even though they are not consistent. So I think there's still a lot of open questions here, but I do believe there are still much more potentials to be on these like large language models in terms of like extracting knowledge from them without even going into multimodality. Regarding multimodality, I think for some type of applications like grounded learning, robot planning, these kind of things, I do think there's strong motivations to incorporate other modalities like the grounded environments or the visual signals. But it's probably application dependent right now.
Thanks, many thanks. Let's see if we have questions or comments from the audience. Any question? People seems to be very shy today.
I think it's people might be too hungry or they are having dinner right now.
Maybe too tired here in Europe because of the hour. But okay, I have another.
I saw like a one raise handle.
Yeah, I think so.
Luis,
yes.
Go ahead. Yeah.
Thank you for the presentation. Very interesting. I hope that we can have the slides to go deeper because there are many references here that we may need to read at some point. But my question is related to representation of this common sense reasoning. Currently, basically, the common sense or the data sets that we have is the concept net. But I probably there are a few more, but basically this is the most important resource that we have. What about representation of this knowledge? Because in some of the experiments that you show us, is basically information that is implicit inside the transformer or the model. But what about having this information outside and being able really to in-deep this information inside the system? Do you have any thoughts about how datasets should be created or what kind of new datasets should be created and how we can represent better this information? Because in my current understanding of this, triplets may not be the most useful or more reliable or complete kind of information that we need for common sense. So what are your thoughts
exactly.
on representation?
Yeah, I mean, I think that's a great question. I guess this is still an ongoing sort of discussions in the community regarding like what is the right form of representations for this common sense knowledge, or if we should even try to construct a knowledge base or knowledge graph to capture that. My personal take on that is like I don't think we have to construct a repository or knowledge base for this knowledge to store everything out, which is almost impossible because the amount of knowledge is just so it's just exponential. It's not able to be computationally affordable to store them. I think ConceptNet was a great effort, but as we build larger and larger language models, the benefit of ConceptNet start like diminish. In many cases, we found it language model already understand what ConceptNet has. So I think that's a kind of a big trend where like this human curated or like a web or like a crowdsourced knowledge repository wouldn't capture the speed of understanding knowledge compared to big language model. But I do agree that there's still gonna be a mechanism of like externalizing what the knowledge and the inference rules the model is using on the particular scenarios when they give you an answer. So that externalization process can be done by, for example, generating free text rationales or explanations, and then expose those reasoning process into natural sentence or into some other more structured representations like first order logics, for example. I think those might still need it. That's my take. Yeah.
Thank you, Rian. Xiang.
Thanks.
Good. More questions from the audience? Nope. I have another one. If you don't mind, we can exploit you right
Sure.
now. You're in the morning, so you still have some time here. But yeah, it is the relation you mentioned now about the first order logic. So kind of neurosymbolic combination. I don't know exactly how to say that, but because the language models maybe are answering yes to a positive question and also yes to a negative, the same negative question. So including no, because they don't understand very well what is true and what is false. No, so how can, so it's totally I think unsolved question, but how we can maybe combine both approaches, or trying to see how large language models can be coherent in the sense that answering yes to a positive question and saying no to the negative, they should be aware of that. So and it seems that it is not the case.
Yeah. I mean, that's actually a big directions we trying to pursue in my collaboration with AI2 and Yejin's group right now. Our proposal there was like we should have a two representations. So the language representations we are talking today, which for example the encodings from large language model, these representations, they are definitely tied with the surface forms of the language. For example, are you using these words versus the other synonym word, or is this or like paraphrase one and paraphrase two should have different language model representations. But the underlying logics, the reasoning logics, they should also have a representation, and that representations will be invariant to these surface form changes, like in Ricard. Those couple perturbation sentences, we will hope them to have a close representations on the logic space. So our kind of envision there is to have a logic-based representations, which is a layer lower than the language representations produced by language model. But the challenging thing is like you need to find data at a very large scales to learn these logic representations. So even for the case of Ricard, the data constructions are semi-automatic by first manually create these first order logic forms, like object A size is smaller than object B, then likelihood of B in the container is larger than the other. These things need to be first created with some logical templates and then plug in those entities using concept map and then translate them into natural language sentence by doing some paraphrasing. It's a very artificial process right now. So we don't believe that this data will be sufficient for learning the logic representations that are as expressive as our current language representation. But this is like a directions we are trying to investigate and trying to see if it could happen.
Thank you very much for the answer. I think, yeah, it's plenty of future research directions here. So it's for sure there will be a lot of PhD students and doing research here, hopefully. So last chance for a question to Xiang. If not, I think we can stop here if you want. I have one additional question, just because this is we are quite very keen about different languages, multilingual, so multilingual language models. So also cultural bias, no? And it seems that common sense there is only one, and it could be many of common senses, no? Different languages, different cultures. And I think we are not doing much research on that. So it seems that there is only one. You know, so the common sense, which is world knowledge most of the times, but not only. And what do you think about that? I mean, which kind of approaches we should address?
Yeah, I mean, I think there's actually strong connections between multilingual learning and common sense reasoning. Like, actually, we have a paper last year on like understanding the common sense through multilingual learning, because by definition, common sense, that's actually a very interesting open question. Like, common sense should be culture dependent or language dependent. And we already see like there's biases across different cultures, like perceiving the same piece of knowledge differently. Other than that, a big amount of common sense knowledge should be shared across people in the world, right? Across different cultures. So it's a very interesting question of like, if we can align the representations and align the knowledge across different languages, then we will be able to extract common sense knowledge across data of different languages. That's also pretty exciting directions. We have a called X, meaning cross-lingual X CSR datasets, which is created for over 10 different languages on the same task formats. And plus, we also show like cross-lingual alignments is actually helpful for improving current language models like MBERT or XMLI for solving this task. Yeah.
Thank you very much. I think we are going to have a look at these data sets, which looks very promising. So thank you very much again. Thanks, Xiang. Thanks the audience for participating and being here. And just to let you know that the next talk will be on the 3rd of November, so by Berit Swartz, which also she's research is about common sense. So we are addressing this topic in these two parallel and also related seminars. So we invite you to attend that seminars next month. And let's say thanks again to Xiang for his presentation. Very interesting and very exciting moment for common sense reasoning, and with large language models and all this material, also not only language but also visual, all these multimodal models. So thank you very much again, Xiang, and thanks for participating, and thanks everybody.
Yeah, thank you for having me. Bye guys. Have a good night.